We're looking next in section 7.3 at how to find the integrals of expressions that involve powers of trig functions. We're going to be looking at essentially certain types of situations, I guess I should say. We'll be able to integrate powers of a single trig function, like sine cubed of x or secant to the fourth of x. And then we'll also be able to integrate products or quotients if they involve either sine and cosine, secant and tangent, or I'm going to say cosecant and cotangent, although I will say this one is just like secant and tangent. We'll actually do the secant and tangent. We won't do these, but the exact same techniques that are used here can be used here as well. All right, when we look at these, I'm going to say m and n are, I'm going to put the word positive in parentheses, positive integers. It's actually okay if we use m and n any real numbers. But generally speaking, the positive integers are the easiest ones to work with. So we'll look at those at least first. In order to do this, we're going to need to make use of our trig identities. These are all on your list, but I just kind of separated them out here. The ones that we'll be using the most are these, the three Pythagorean identities. These two, it says half-angle identities, and they are, but they've been solved for sine squared and cos squared. So I'm just going to mention on your list that I gave you in your pack, these are listed as power-reducing identities. They're just the half-angle identities solved for sine squared and cos squared. And then these down here. So these, what is that, 9 or so, 8 or 9, I guess, identities are going to be frequently made use of as we do these problems. All right. Basic idea with most of these is going to be to organize our integrand so that we can make just sort of a handy u substitution and then get a nice easy power rule problem out of it, which we all know how to integrate very simply. So we're going to start with the ones that involve sine and cosine. And here's our strategy. You, by the way, do not need to memorize this, even for final exams or anything like that. This is on your list. You'll probably notice that on your list of formulas that I gave you. When it comes to the unit 3 is what I'd be looking for here. In addition to integration by parts, these exact same tables that you're seeing here are on here. So you just need to know how to use them. All right. So the strategy that I use is going to depend on whether m and n are even or odd. In our first example, we have sine to the 5th power of x. Notice then m is 5, so m is odd. And it says split off sine x. So I'm going to start by just saying, all right, there's sine to the 4th of x, and then I'm splitting off the extra sine x, like so. We now have a resulting even power of sine, sine to the 4th, and we're going to rewrite that in terms of cosine. And in order to do that, this is where I'm going to start using some of my nice identities. So, first thing I'm going to do is say sine to the 4th is really sine squared squared. And sine squared? Right here, sine squared would be 1 minus cos squared. So I've got a really common substitution here. I've used my Pythagorean identity to replace sine squared with 1 minus cosine squared. All right, I'm going to go ahead and I'm going to make my u substitution actually right now. It mentions it in the technique, but notice that it says that you want to go ahead then and use u equals cosine x. So we'll do that. du then is minus sine x dx, and minus du is sine x dx. Therefore, that will be replaced with a minus du. So my new integral is going to be 1 minus, that's u squared, and then this becomes a minus du. All right, in order to integrate this, I'm going to multiply this out. That's 1 minus 2u squared plus u to the 4th. And here's, again, remember our strategy. Our goal was to get it to the point that we could just use power rules, and here we are. Let's see, I'll just keep the minus out in front for now, in front of everything. Integrating du would give me u minus 2/3 u cubed plus 1/5 u to the 5th plus c. And I'm going to replace the u's with cosine x, and I'm going to go ahead and distribute that negative while I do this. So negative cosine x plus 2/3 cosine cubed x, and then a minus 1/5 cosine to the 5th of x plus c. Okay. So with an odd power, you split one of them off, take the even power that's left and use your trig identity on it. And then with a u substitution, we should be able to finish it off just with simple power rules. Let's try a couple more. All right, in example 2, we once again have an odd power on the sign. So I'm going to split off one of those signs. I'll make it sine squared x cosine to the 4th x times the extra sine x dx. And then a very, very similar process, right? We're going to go ahead and say, I want to turn everything into cosines except for this little extra sign that I split off. So I'm going to once again replace sine squared x with 1 minus cosine squared x. I then have that cosine to the 4th of x times sine x dx. I'm saving that to be the du. Right? Everything else is now in terms of cosines. So again, let's let u be the cosine of x. And the derivative would be negative sine x dx, or minus du equals sine x dx. So that right there is my minus du. And I have the integral of 1 minus, that would be u squared, times u to the 4th. And then I replace that with the minus du. All right, let's see. This one, it looks like I'm just going to need to distribute. So I would have u to the 4th minus u to the 6th du. And then I can use just a standard power rule. I'm going to distribute this minus as I go, so it'll be a minus 1/5 u to the 5th and a positive 1/7 u to the 7th plus c. And then finally just remember that u is actually cosine x. And here we go. All right, how about example 3? In example 3, it's the cosine that's the odd power. So we're going to split off the cosine. So I'm going to keep the sine to the 6th of x, and then I'm going to make that cosine squared x times cosine x dx, saving that to be my du. And just like before we wanted everything to be sines, now I want everything to be, before I wanted everything as cosines, now I want everything sines. So I'm going to leave the sine to the 6th the way it is, and then I'm going to replace the cosine squared with 1 minus sine squared of x. Same identity, just solved a different way, right? It's the same Pythagorean identity. All right, so this time, u is going to be the sine. And so du, derivative would be cosine x dx, which is exactly what we've saved right here, so no problem. And so we've got a u to the 6th times 1 minus u squared, and that just becomes du. All right, once again, I'm going to distribute u to the 6th minus u to the 8th, which gives me a form that I can integrate easily just using power rules. So I'd have 1/7 u to the 7th minus 1/9 u to the 9th plus c, or plugging back in u is sine x. I would have 1/7 sine to the 7th of x minus 1/9 sine to the 9th of x plus c. All right, up until now, all of our powers have always just been positive integers. And I did mention that those are usually the most straightforward ones, but it's actually not that much more difficult to do when you have non-integer powers. If you take a look at example 4, you'll notice the power on that sine is actually -1/2 since it's in the denominator. We can handle that as well. Same technique. I'll start by noticing I have an odd power on the cosine, so I'm going to split off a cosine. So let's see, I'm going to actually write that as sine x to the -1/2 power, and then cosine squared x times that split off cosine x dx. Just like the last time with an odd power on the cosine, I want to turn everything into sines. So I'm going to replace this cosine squared with 1 minus sine squared. The only exception is that split off cosine that I'm saving to be the du. So here we go, cos squared x becomes 1 minus sine squared x using the Pythagorean identity. And I can go ahead and make my u substitution. We'll let u be sine x. So du is cosine x dx, which we've saved for ourselves right there. So my integral becomes u to the -1/2 times 1 minus u squared, and then that cosine x dx becomes the du. I can now distribute just like in the last couple of problems. So I'd have u to the -1/2 minus, when I add those exponents, u to the 3/2. And we use our standard power rule again. That becomes u to the +1/2. Dividing by a half is the same as multiplying by 2/1, or just 2. Minus u to the 5/2, And again, instead of dividing by 5/2, I'll just write times 2/5 plus c. And then last step, u is actually sine x. So that's really a square root. 2 square root sine x minus 2/5 sine x to the 5/2 plus c. All right, so every problem that we've done so far, we've had the advantage that one or the other, either the sine or the cosine, had an odd power. When both powers are even is where things tend to get a little bit more challenging, shall we say. And I keep meaning to take one of these out because there's too much stuff on this page. So I'm going to tell you ahead of time just so you know how much space you have. We are not going to do example 6 at all. So you can use the space all the way down here. Example 6 and 7 are almost the same, and so we'll be fine with just doing 7. All right, so here we are. We've got a situation in which we've got a sine and a cosine, but this time they're both even powers. So I don't have one to split off. Back to the strategy. If m and n are both even, this is where we wanted to use those power reducing identities. And our ultimate goal is to get everything to become a polynomial in cosine 2x. Okay. So let's see what we can do. First of all, when I think about those power reducing identities, these guys here, they're for sine squared and cos squared. So my first goal is to get just sine squareds and cosine squareds. So I'm going to think of this as sine squared squared times cosine squared. Okay. This is where I'm putting in the power reducing identities. Sine squared x can get replaced with 1 minus cos 2x over 2. And that gets squared, times cos squared x, that's 1 plus cos 2x over 2. All right, we've got a little bit of algebra to do. I'm actually going to cheat just a little bit here. Not really cheat, but I'm going to make my algebra easier, which is a good thing, right? First of all, I'm going to notice 2 squared, or 4, times 2 is 8. So I'm going to pull the denominator out and just put a 1/8 in front of the whole integral. Okay. I'm then going to write one of these 1 minus cosine 2x's. And then the other one from the square, I'm just going to multiply these two together because that nice difference of squares is going to help me out. So I would get 1, outers and inners would cancel, and then a minus cos squared 2x. Okay. That now isn't too bad. I'm going to go ahead and multiply that out. So I have 1 minus cos 2x minus cos squared 2x plus cos cubed 2x. Okay, the first two terms are pretty straightforward. I can deal with those. So let's do those first two. I have 1/8 times. Integral of 1 is just going to become x minus the integral of cosine 2x is sine 2x. And this is one of those little u substitutions, right? If u was equal to 2x, then the derivative would be 2. And when I bring it to the other side, it's going to put a 1/2 on here. Okay. So, got those first two terms done. Then I've got minus, and I'm not going to be able to do this integral yet, so I'm just going to write it out, minus the integral of, whoops, cos squared 2x dx plus the integral of cos cubed 2x dx. So I've got two more integrals that I need to worry about or figure out. This one, because it's already a cosine squared, I could just go ahead and use this power reducing identity again. I can just replace it with a 1 plus cos 2x over 2. Haven't done the integral yet, just used a trig identity. This one, because it's an odd power, we're going to use our technique where we split off the extra odd power. So I'd have a cosine 2x dx out here. And then the other cosine squared, we want to make that into a 1 minus sine squared 2x, just like we were doing in the previous examples. All right, let's keep going. Let's see, that's a 1/2. I'm going to pull that out. And then integrating this is going to give me an x plus, here it is again, the integral of cosine 2x is sine 2x. But I'd have a little u substitution on the 2x, which is going to bring a 1/2 out in front. All right, so the first 3 terms are done. Still have to deal with this last one. This is going to require a little bit more of a u substitution, so I'm going to go ahead and write it out. For this integral, my u is going to be sine 2x. So du would be 2 cosine 2x, that 2 from the chain rule, dx. And I'd have a 1/2 du equals cosine 2x dx. So that cosine 2x dx ends up getting replaced with a 1/2 u. So here we go. I've got 1 minus u squared. This becomes 1/2 du. And I won't recopy this over and over again until I kind of get this thing figured out. That's going to be a 1/2 u minus 1/3 u cubed, which would be a 1/2 sine 2x, and then a minus 1/6 sine cubed 2x. And then I'd have all the rest of this in front of it. And let's see, I'm going to distribute that negative 1/2. So I would have negative 1/2 x minus 1/4 sine 2x plus all of that. And then the 1/8 in front of everything. And I should squeeze a plus c in there. All right, as if that weren't bad enough, it looks like I do have a little bit of combining of like terms that I can do. It might actually make it a bit better. I can get rid of those, right? Negative 1/2 sine 2x and positive 1/2 sine 2x. And then I can also combine the x and the negative 1/2 x. So for my final answer, I'm going to have a 1/8 times 1x minus 1/2 x would be 1/2 x minus 1/4 sine 2x, and then a minus 1/6 sine cubed of 2x plus c. All right. If I didn't lose anything, lots going on there. That should be my final answer. Okay, so that's basically the powers of sines and cosines. The last example I have here, and 6 was just like this, and this is not too challenging, so I think you'll be fine with just one example of this last thing. This last example, instead of being powers of sine and cosine, what we have here is sines or cosines or both with different arguments. Anytime you have sines and cosines with different arguments, you'll always use these product to sum identities every single time. So in this particular case, we'd be looking at this one, since we happen to have cosine cosine. And it looks like our alpha is 15x, and our beta is 4x. So I'm going to start by rewriting the integral using this. I'm going to pull the 1/2 right out. And then I have cosine alpha minus beta plus cosine alpha plus beta. So just that identity, and from there it shouldn't be too bad. Let's see here. We have got the cosine of 11x plus the cosine of 19x is our integrand. And again, these are just those little bitty substitutions. I'm going to try for us to do them mentally. The integral of cosine is sine, in this case of 11x. But when the u was 11x, the derivative would have been 11, and we would have ended up dividing that to get it over to the other side. So I'll have a 1/11. And same exact argument here. We've got the integral of cosine 19x, which would be sine 19x. But part of that little u substitution would have been a 1/19 on the du. Oh, we can leave it just like that. By the way, on both of these, I don't mind if you've got like a factor like this factored out. You can distribute it through if you want to, or you can just leave it factored out. Doesn't matter to me. Either way works. All right, so that's sines and cosines. I think we'll come back in the next video and deal with the secants and tangents.